Okay, I'm recording this lesson now, and we're going to speak about basement insulation, or the thermal behavior of a basement. Well, this is a good detail. This detail is taken from that book, The Builder's Guide to Cold Climates. I told you that we are not designing details, or maybe we will be designing details by the end of this semester, but we're not designing details on our own. We are copying good details. So all details that you can find on that book, those are good ones, so you can copy them. This is what I have done to explain this. So I have copied this. What is the relevant thing about this detail? As I told you, we have a basement here. We have to protect this basement against water, infiltration of water. So if it rains here, this is the soil outdoors. So if it rains, the water will filter. And here we have this drain. So part of the water that it's here will go through this drain, and then we will get rid of it. If it hits the concrete wall. Concrete is something that bears water, not forever, but it's better than brick or natural stone. So I think concrete is for basement walls, concrete is the right option. And then after that, we have the thermal insulation inside. We can have thermal insulation outside as well. Inside is easier because working outside, we have to dig this, and then we have to place a lot of stuff here, but people will be working, the workers here will be working in a trench. Is it safe? Well, it's safe, but there is always a risk that if the earth moves, you can, yeah, so it's risky. So working inside, it's always safer for people working. And so do I recommend inside thermal insulation? Yes, I do, but for safety reasons. But another important thing is that you see that here we don't interrupt the thermal insulation. Here we have the slab, and this is the critical point here. So the most important thing is that we don't interrupt the thermal insulation. Okay, so we have to figure out how to do this. So that's why at the beginning we have to copy good details, because trying to solve this on our own, it's difficult because there are a lot of things to consider. So by copying good details, we will end up internalizing what a good detail is. And this is good because we don't interrupt the thermal insulation. So this is the rule number one when it comes to designing good buildings or good details. Do not interrupt the thermal insulation. So here we have the wall thermal insulation, we have the slab thermal insulation here, and finally we have if this is a basement, because we are talking about today about basements with thermal insulation and with the comfort temperature. Okay, so we can say that the temperature is 72 Fahrenheit when the outdoor temperature is 20 Fahrenheit. Okay, this is not a crawl space anymore. So that's why we don't, if we have this basement with the heating system here, we don't need thermal insulation on that slab because the temperature here would be 72 and the temperature here would be 72. Okay, so we don't need thermal insulation here. We need to protect the basement, the heated space. We need thermal insulation because the heat will go in this direction. Okay, so now we have to understand how it works. We have the indoor air at 72 Fahrenheit here, and the outdoor air at 20 Fahrenheit. So the air, the heat, not the air, the heat tends to go from the warm space to the cold space. What happens? So imagine that we have this position here. The heat doesn't go horizontally in this case. Let me Okay, so this is the wall that we have already studied. So here the heat flux is horizontal because it goes from 72 to 20 Fahrenheit. So the shortest way to go from this point to that point is a straight line. But here, this is not the shortest way because this soil continues. So the heat goes that way. Okay, so the heat that we have at this point, if it wants to escape, it has to go through the wall and it has to go through all this amount of soil that we have here with a line like this. And we can do that in different positions. Like this. Okay, so now the heat has to go from this place inside to that place outside. So this is the path that the heat will follow. Why? Because it's the shortest one. It doesn't go that way and then, no, it goes the shortest way. But the shortest path from this point to outdoors is longer than this path from this point to outdoors. So what does it mean? That we don't have a thermal resistance. We have a thermal resistance of this wall, but then we have to add the thermal resistance of the soil. And the thermal resistance of the soil is different because the thickness of the soil is different in each point. Okay, so this is what ARCH260, because I'm taking this from ARCH260, this is what ARCH260 well, this is what ARCH260 is teaching us. So this is a slide, or this is a picture taken from the ARCH260. So look at this. If we are here, this is not a straight line. Okay, so it's not straight. It's not a straight. It's like a curved line. Okay, so all these isothermal lines are not straight, but we can assume, or we can make this assumption that this is like a straight line. Okay, so it's curved, but the mistake that we're making is not a lot. But look at this. If we are losing heat through the floor, but the amount of heat that we are losing through the floor, it's almost negligible, because first, the heat tends to go up. Okay, so if we have heat here, the natural way to lose that heat is going up through the wall. We can lose heat, so some part of that heat can go down, but then look at this. It has to go through a lot of soil. So the thermal resistance of that soil, it's very high because of the thickness, not because of the thermal conductivity, but the thickness of that element here, of the soil that we have here, is a lot. It's very, so we won't have a lot of heat losses through the floor. So that's why usually when we are working on basements, we don't have thermal insulation on the floor of the basement itself. Why? Because the path from here, from this point to the outdoors, it's very long, and well, if the heat tends to go this way, so that's why the most important thing is the wall in basement. It's not the floor. Okay, so first, after looking at this, having thermal insulation on floors, it's not necessary. Here, as you can see, we have something. This is a good detail. So here we have something that it's a vapor barrier. Okay, this is different. It's not thermal insulation. It's to protect the basement from water. Okay, because there can be water underneath our building, and the water can end up yeah, end up entering our buildings. So we need we need a water barrier to prevent water from entering the building. So, and here we have two enemies here. We have the heat losses and we have water. We have to prevent heat from going out, and we have to prevent water from entering the building. Okay, so those are our enemies. The heat wants to escape, and the water wants to enter the building. So that's why we need thermal insulation, and we need a waterproofing here. On the floor, we don't need the thermal insulation, but we do need the waterproofing element. Well, that's the theory. Now what do we do? Well, this is the same. Well, ARCH well, divides this wall into different slices. Okay, so you see that we have 1, 2, 3, up to 12 different slices, and each slice is 1 foot. Why? Because this is what ARCH says. We can divide this in smaller thicknesses, but ARCH says that a foot is good enough. Okay, so okay, I will calculate the thermal resistance of that foot, and then a foot below, and then a foot below, up to the total height of this basement wall. And then the heat flow goes through this path with an angle. This angle is, let's say, uh, 45. It's not a straight line with a 45. It's something like this. Okay, so it will be a curved line. It's not straight, but we are making that assumption to make things easier. So this is what ARCH says. Okay, so we have to calculate, we have to divide this wall into different slices, and each slice is 1 foot height. And then we have to calculate the heat flow through this path. And we have to calculate this 1, 2, 3, 4, 5, up to 12 times if we have a 12-foot wall. If we have a 6-foot wall, we have to calculate it 6 times. So we have to divide this into different slices, 1 foot each. Okay, so now I'm going to try to explain this drawing. So I'm going to explain everything that I have mentioned before, but by drawing things, I think it will be clearer. Okay, so this is the basement wall. This is a footing. This footing is a structural element. You have seen that we have different, or we have the wall. This is a concrete wall, yeah. And this is a footing because, well, it's the structural element. We need a transition between the soil and that vertical wall, and this is what a footing is. If you take statics next fall, I think they will show you why we need footings on buildings. Anyway, this is the wall, this is the footing. The footing is a structural element. This is the soil. This is this hatched area is the soil. So we will make this grayish because it's a reinforced concrete. This is a usual material for basements, reinforced concrete. And here, above grade, there will be the thermal insulation. Okay, so this is the wall that we have already studied. A wall with this thermal insulation, with this hatch of the thermal insulation. Okay. And now, okay, this is the wall. And now we have to divide this wall into different slices here. Each slice a foot. So here we 1, 2, 3, 4, 5, 6, 7. Okay. So this is a 7-foot wall for a basement. I think 7 feet is good. And now this is the soil. I will use another color. Okay, there you go. This is the floor, the first floor slab, and this is the basement floor. I told you that we don't need thermal insulation here. So what we have underneath that flooring or that slab is soil, okay? So it's more soil like this. Okay, so now we have to divide, or we have to create those lines with the angle is 45 degrees. So from all these points, we have to go up because this is the path that the heat will follow when the heat tries to, when the heat wants to escape or wants to get out of the building. So those are different paths, and those are parallel lines. And each layer is, or each slice is a foot. So we have 1, 2, 3, 4, 5, 6, 7 feet. Okay, so we have divided this wall into 7 different parts. This is the outdoor. This is air. I don't like this. I'll do it again. Okay, this is better. Okay, so this is the outdoor air. The temperature here, if it's winter, that would be 20 Fahrenheit. And indoors, there will be 70 Fahrenheit. Okay, now we have to apply thermal insulation to that wall. Okay, according to ARCH260, we can interrupt the thermal insulation here. I don't like it, and I will explain you why, but this is the problem that we are going to solve now. Imagine that we have only 3 feet, or the height of the thermal insulation, it's 3 feet. And then the rest of the wall is uninsulated, so we don't have any thermal insulation. So the first 3 feet, we have thermal resistance with thermal insulation. And then the rest of the wall is 4 feet. We have an uninsulated wall. Uninsulated. Okay, and then I'm going to, just to complete the detail, so I'm going to draw the structure of that slab. Okay, so here there will be rafters. Those are the rafters. And between the rafters, there will be fiberglass. We don't need thermal insulation because the temperature on the basement is 72 and the temperature on the first floor is 72. But even from the acoustical point of view, it's good. Having fiberglass between slabs, it's something good. Okay, so this is the first stage. We have defined the wall. It's a 7-foot wall, basement wall. We divide this into 7 slices of 1 foot. We apply thermal insulation here only on the first 3 feet. And then we have to calculate the thermal resistance of that this thermal insulation. So let's do this now. Okay, so we have to calculate the thermal insulation, or the thermal resistance of that thermal insulation. Imagine that we are using EPS, expanded polystyrene, as a thermal insulation and we use only 1 inch. Okay, so if we go to lesson 3, 1 inch, it's the thermal resistance of an inch of extruded polystyrene is 5. 5 what? We have to write down the units: hours, feet square, and Fahrenheit, divided by BTUs. Okay, so this is the problem. We have the R value of the thermal insulation here is 5. Okay, the temperature here would be well, 20 Fahrenheit is outdoors. Indoors, it's 72. Fahrenheit. And what's next? And we have 3 feet with thermal insulation, with this thermal resistance, and 4 feet of an uninsulated wall. So we don't have any thermal insulation here. The same thing that ARCH is, so here we have thermal insulation, then we interrupt the thermal insulation, and we have an uninsulated wall here. Okay, so here we have the same thing. Okay, so this table is taken from the ARCH. This table is taken from the ARCH, and well, I have taken that table and have turned units into the imperial units because I don't want to mess up things. Because even the ARCH, which is the American heating and air conditioning engineers of America or whatever, it's an American institution, but they are using international units for tables and calculations and that stuff. So that makes me think that in a few years, maybe 50, 100, or 2,000 years, the world will converge into the international units. But this is what I think. Anyway, I have turned the units here, and I have divided this table. So we have 7 different rows, and each row it's a foot. So this is 0 to 1, 1 to 2, 2 to 3. So this is the depth in feet. Okay, so those are the units of that table. We don't need that column, I think. Yeah. Okay, so we're not going to use that column, but we're going to use these 4 columns: 1, 2, 3, 4. The values we have here, we're using, by the way, the white columns. The gray columns, well, we're not going to use those values, although we might need those values in the near future. But today we're going to use only the white columns here. And here we have divided this into 4 different columns. The uninsulated wall, so when we don't have any thermal insulation on the wall, we have to use those values. And these are different thermal resistances. So here, this is 4, this is 8.3, and this is 12.49. If you remember our problem, the thermal resistance of our thermal insulation was 5. Okay, so if our thermal resistance is 5, we have to select this column here. So we have to go to the lower one. So even if we had 8.1, we have to select this column because the value here is 8.3. Okay, so we have to, so we don't have to select the column with the closest number. We have to select the column with the lower number. So if we had 10, we have to use this. If we had 20, we would have to use this one. But if we have 5, we have to use this one with 4.14. Okay, so what have we done? We have a thermal resistance. The thermal resistance of the first 3 feet of our wall is 5. So we are going to take these values, 1, 2, 3 feet. So we're going to select 1, 2, and 3 values here. The rest of the wall is uninsulated. So we're going to select this column. As of the 3rd foot, I have to select this column here. Okay, so I would select these 3 values for the first, I'm going to use these 3 values for the insulated part of the wall, and I'm going to use these 4 values for the uninsulated part of the wall. Okay, I have here, okay, so this is the same table. So the insulation is here at the top of the wall. Well, first our R value is 5, so that's why we're selecting that column. And we have thermal insulation only 3 feet. So this is the part of the wall with insulation. And then the rest of the wall is not insulated. So we have to select the first thermal transmittance, it's 0.15. The second will be 0.12, and the third would be 0.09. And then the rest of the wall without thermal insulation, I will select not this column, nope, that one, because this is the uninsulated column or the uninsulated wall. Okay, so now I have to divide this. I have to select 7 different U values. So the first one is 0.15. The second one is 0.12. And the third one is 0.09. Okay, so these 3 values here. Then the rest of values are uninsulated walls. So I have to select that column. So the first one is, the fourth one is 0.12. The fifth, it's 0.1. The sixth, it's 0.02. And the seventh, it's 0.07. Okay, so now I have to calculate 7 different thermal loads. This is for the insulated part of the wall. And I start a new drawing now. Okay. Imagine that I have this wall. This is the basement wall. I'm drawing as a perspective now. And I have divided this into 7 different slices. So this is a 7-foot wall. So I have 1, 2, 3, 4, 5, 6, 7. Okay, this is a footing. There you go. And now we have divided this into 7 parts. We have thermal insulation only there. Three feet with thermal insulation. and 4, 5, 6, 7 without thermal insulation. Okay, so now each slice has an area. The height of this part of the, I'm hatching this part of the wall, so the height is 1 foot, and this is the area 1, okay? Then the second, and the height is 1 foot. And we have a length, so the area is 1 foot times that length. Then the second slice, I will use a different hatch. So this is area number 2. And so on and so forth. So we have up to 7 areas because we have 7 slices. Then I have to calculate the thermal load. So this is the thermal load of the first slice. So it's the U value of the first slice, which is 0.15 times the area of the first slice times indoor minus outdoor temperature. Okay, then the second, it's the same. The U value of the second slice, the area of the second slice, and then 1 minus indoor temperature minus outdoor temperature. And so on and so forth. I have to do this 7 times. The first 3 U values come from that table with the thermal insulation, with the thermal resistance R equals 5, and the 4th, 5th, 6th, and 7th come from the same table, but from the uninsulated column. And finally, Q7. Okay, and now I have to add them up. Okay, so I have to calculate each Q1, 2, 3, 4, 5, 6, 7, and I have to add them all up. And what's next? Now imagine that we are working with our basement. Okay, so there's a rectangular building, and this is the basement now. So let's say that the length is 25 feet and the width is 20. It depends on your ID, but it's a rectangle, something like that. And this is the thickness of the wall. Okay, this is the basement wall. And now I have to divide this basement into different slices. Here, I don't have just the wall. I have the 4 walls of the basement, the north, south, east, and west. So I'm hatching the first slice of that wall. Okay. So this is the first slice, and I have 4 walls. So this is 1, 2, and 2 more. The thickness or the height of this slice is 1 foot. But remember that I have 4 different slices, so I hatch this and that one. Okay, now the second slice, it's here. Okay, and we have 4 walls, sure. 3 and 4. And this is 1 foot. Great. What's the area now? The area is a foot, this is the height, times the perimeter of the wall. It's 20 plus 25 plus 20 plus 25, because we have 4 sides of this rectangle. So it's 20, 25, that one will be 20 again, and that one will be 25 again. Okay, so here I can type, this is 20 feet, and this is 25. Okay, so the area of this slice, it's 1, because the height is 1 foot, and then the perimeter, it's 20 plus 25 plus 20 plus 25. So this is the area. The area of all these slices, it's always the same. It's very unlikely that we have a basement with different shape in different walls. Well, it might be, but in this case, we have a rectangle. We have to calculate the thermal load of the basement. So what is the thermal load? Q basement equals, it's always the same. It's the U value times area times indoor minus outdoor temperature. So U1, it's 0.15. A1 equals 1 times 20 plus 25 plus 20 plus 25. So this is 50 plus 40, this is 90. So the Q value Q1 equals U1 times this. So that would be equals 0.15 times 90 times indoor minus outdoor. It was 72 minus 20. This is Q1. The second 2 equals, it's not 0.15, it's 0.12 and then 0.09. So that would be 0.12. The area is going to be the same, and the indoor minus outdoor temperature is the same. So it only changes the first U value. Then the third one, 3, is 0.09 times 90 times this. Then the 4, we have the 4, the 5th,
the 6th, and 7th. So this is not, okay, this is 0.09. Let me see. Okay, it's 0.12, 10, 8, and 7. So it's 12, 10, 8, and 7. So we have to calculate this, and then we have to add them up. So that equals whatever, and then we have to add Q1, 2, 3, 4, 5, 6, 7. And this is the thermal load through the basement. So first, we have to calculate the thermal transmittance at different levels. Okay, so we have to calculate, this is U1, that would be U2, that would be U3, 4, 5, 6, 7. Then we have to calculate the area, but the area of the basement. And so if we are dividing this into slices, into 1 foot slices, so this is the height, which is always 1 foot, times the perimeter, and the perimeter of the basement. If we have a 20 by 25 rectangle, so it's this 20 plus 25 plus 20 plus 25 as well. Yeah, so the areas are going to be the same. The area of the first slice is the same as the area of the second slice, because it's always a foot times the perimeter. The U value is different. So now I have to calculate the thermal load with the U value. The area is always the same, and the temperature, indoor minus outdoor temperature, is always the same, 70 minus 20. Okay, so only these values change. And the values of the thermal transmittance, they come from this table, depending of what part of this basement has thermal insulation. So if it's uninsulated, we have to take values of this column. If it has a thermal insulation close to 4, we have to take the values from that column. In my opinion, this is too complicated, so I wouldn't do that. Anyway, this is what ARCH260 says, and that's why I'm explaining this to you. But first, there is no point in doing this. So go ahead with the thermal insulation. And go ahead, and I would say that you can use the same thickness of thermal insulation that you would use for the rest of the wall. So you can use 6 inches. It pays off, believe me, because thermal insulating materials are not expensive. And if you are really going to use this basement, it's worth having thermal insulation from the ceiling to the floor. Anyway, if we want to do that, that's the way ARCH260 recommends calculate this thermal load in the basement. Why do we divide this into a foot slices? I don't know, but this is what ARCH260 says. This is something that probably it will change. We need to know the concept of this. So the concept is that we need thermal insulation, that the thermal insulations the thermal loads through basements are not critical, because we have the earth or the soil that we have around us help us keep this basement at a temperature close to comfort. So it's not an issue. We don't need thermal insulation on the floor. Why? Because the path for the heat from the indoors till outdoors, it's too long, and so we have a lot of earth here. So there's a lot of thermal resistance as well. So we don't need thermal insulation here on the floor, but we would need thermal insulation here on the wall. And if you want to decide where to place, if you only have a limited budget and you can place only 3 feet of thermal insulation, okay, do it here on that corner. Do not do it here at the bottom, but at the top corner. Okay, so this is what ARCH260 wants to, but it's too complicated. I don't like this method, but this is this is what ARCH260 recommends, and who am I to criticize ARCH260? Okay, what do you have to do now? You have to continue to calculate this. So imagine that we have a basement on that building. Okay, so you have to use your ID again. So you use exactly the same dimensions you used for the previous exercise, but now you have to give the basement. And the basement, it's 20 plus x wide by 20 plus I long. So this is the perimeter of the basement. And then we have a 7-foot basement below grade. Okay, so the height of the basement is 7 feet. The same thing we have done here. And the R value is 3. I didn't want that. Okay, no. That will be 9. Okay, so only 9 apply to the top 1 foot of the wall below grade. Okay, so in this case, we don't have 3 feet, we have only 1 foot, but the thermal resistance of that foot is not 5, it's 9. So if it's 9, we have to select this column. Okay, so the first U value would be this one, and then the following values, we have to take the uninsulated column because we don't have any thermal insulation below 1 foot.